Okay, welcome back with another video of equivalent series. Today we'll be looking at the next equivalent we have in our syllabus, that is equivalent EMF. What is EMF? Equivalent EMF is equivalent electromotive force in cells, right? Okay, the basic theory part here is, right? Basic theory involves here is, if there's only single cell, we know this terminal is plus, the shorter terminal is minus. Always current flows out from the positive terminal like this. Current flows out from the positive terminal and current flows in to the negative terminal for a single battery, single cell, right? So when current flows in, voltage difference across the cell, let's say A and B, voltage difference across the cell is defined as E minus IR if EMF of the cell is E and resistance of the cell is R. Internal resistance. Resistance of the cell means internal resistance of the cell. Right? If EMF of the cell, electromotive force of the cell is E and internal resistance of the cell is R, right? Potential difference across the cell can be written as VAB equals E minus IR. Right? VAB equals E minus IR when current flows out from the positive terminal. Got it? Okay, now this is a respective theory part. Now using this, let's see how series combination of cells work. Right. See, series combination. Let's consider 3 cells in series combination like this. 3 cells in series combination like this, connected between A and B. Connected between A and B. Right. When it comes to cells, the method, the approach that we are using to solve equivalent is a little bit different. So therefore, this is going to be a kind of a different video from the other videos you watched before. Right. Let's see. Let's say this is E1 with internal resistance R1. This cell is E2 with internal resistance R, let's say R, and E3 with internal resistance R. Right. Then the equivalent cell should be replacing the system between A and B like this. Equivalent cell should be replacing the system between A and B, same points like this, right? Okay, now let's say this system carries, current flows out from the positive terminal, no? Like this. So let's say this system carries a current I. If there are no junctions, there is same current because no division of current. If there are no junctions, no division of current. Now, if the current carries by the system is I, that same current should be carried by the single equivalent. Same current should be carried by the single equivalent. That's the idea, right? Okay, so let's consider this equivalent as E dash, right? E dash with R dash, right? Equivalent as E dash with R dash, right? Now, according to this equation, look at the board. According to this according to this, V equals E minus IR. According to this, now we know current is same, right? Resistance is also same, internal resistance is also same, but E is different, EMFs are different. When E is different, then potential difference across each cell should be different according to the equation, no? Right? That's the idea. It should be different according to the equation, right? So therefore, see, now this is what I'm trying to do. Look at here. This is what I'm trying to do. I'm going to apply this equation for these cells one by one separately. See, for these cells separately. What is our equation? V equals E minus IR. V equals E minus IR. Right? So let's apply this for these 3 cells separately. Let's apply this for these 3 cells separately. First one. Right? Let's consider these potential differences are as V1, V2 and V3, right? And this total is going to be what? VAB, between A and B, VAB, right? Then for first one, V1 equals according to the equation E1 minus IR, right? For second one, V2 equals E2 minus IR. For third one, V3 equals E3 minus IR. Right? Now, similarly, if I use the same for the equivalent, what I can write is VAB equals E dash minus IR dash. Right? Now, we can do something like this. We know VAB, total potential difference across points A and B, is represented by V1 plus V2 plus V3, because VAB is now divided into 3, as a part as V1, another part as V2, another part as V3. Right? Same idea as we had in equivalent resistance. Total voltage difference is the addition of V1 plus V2 plus V3. Same idea we can use. See, then VAB can be written as V1 plus V2 plus V3. VAB can be written as V1 plus V2 plus V3. But we know V1 is E1 minus IR1. So likewise, VAB is E dash minus IR dash. Plug these values. This is E dash minus IR dash. Right? V1 is E1 minus IR. Right? Then V2 is E2 minus IR, and V3 is E3 minus IR. Now, left hand side is E dash minus IR dash. From right hand side, I'm going to take all E's together. Then E1 plus E2 plus E3 comes. Right? And I'm going to take I out, minus I out, and going to write this as here what comes minus IR, minus IR, minus IR. Altogether minus 3IR. Right? Minus IR, minus IR, minus IR, minus 3IR. I'm going to write it as minus I times 3R. Right? Now, same shape is created in left hand side and right hand side of the equation. Now, same shape is created. So hereafter, we are going to do a comparison. By method of comparison, we can compare these two equations. Right? This part to the answer relevant part. A minus sign to minus sign. I to I. R dash to another part. So by comparison, now we are going to find the equivalent. That is what I meant as the difference here in this approach. Right? Now by comparison, this is called the method of comparison. See, by comparison, what we can say is E dash equals E1 plus E2 plus E3, and R dash equals relevant part is 3R. Right? So this is the final answer. R dash equals 3R. That is the final answer. A little bit different approach, method of comparison. Right? Which means if cells are connected in series combination, the equivalent EMF, equivalent electromotive force is increasing. Right? E1 plus E2 plus E3. Equivalent electromotive force increases. And what about the resistance? Equivalent internal resistance, that also increases. Because internal resistance of the cell is, right, it is inside the cell. Now, since you know about equivalent resistance now, you can verify that part. How? Internal resistance of cell E1 is inside E1. Right? Internal resistance of cell E2 is inside E2. Internal resistance of cell E3 is inside E3. Right? These three resistors are in a series combination. No? So we know in series combination, resistance are going to be added. Now, if there is R, it should be 3R. So that is what it's given here. Right? So equivalent resistance is 3R. Equivalent EMF was the part we were interested here. That is E1 plus E2 plus E3. Right? Method of comparison. Hope it's clear. Now let's see what happens in parallel combination of cells. Parallel combination. Right? So this is all about the series combination. Now let's see the parallel combination. See, parallel combination. Parallel combination. Right. Let's consider three cells which are in parallel combination like this. See, three cells which are in parallel combination. Say it's connected between A and B, right? So equivalent is also going to be replacing the system between A and B, right? Equivalent. Let's say E dash and R dash, right? And here these cells are E1, R. Let's say this one E2, R. This one E3, R. Right. Now, we know if there's no electronic device met, all points remain same in a circuit, right? In a electronic circuit, electrical circuit, right? If there's no electronic device is met, simply if you are going through just conducting wires, just the conducting wires, which means points are same, right? So if this is A, up to here that is A, up to here also that is A, up to here also that is A. If this is B, up to here, here and here that is B, right? Now you can see very clearly that all three cells are having the same potential difference, right? Now according to this equation, argue, we know V equals E minus IR, no? V equals E minus IR. R is constant, R is same, constant in the sense R is same, right? And V is now also same, V is also same. We know E is different for sure, E1, E2 and E3. Then if E is different from the other side, I should be different. If E is different from the other side, I should be different. Therefore, current flows across, current flows through each cell is going to be different now, right? Okay, having that idea in mind, let's mark the current flow, right? Let's consider total current which comes into the circuit as I. The same current should go out. But since current flows through each cell is different, I'm going to consider these currents as I1, I2 and I3, right? Let's say this current is I1, this is I2, this is I3. Now this current should be same as the system capital I, right? Now, since difference is with the current flows, right? Difference is with the current. Now I'm interested about the current because different quantity is current now, right? Therefore, from our general equation, I'm going to subject current and apply this in the equation. See, this is my general equation. V equals E minus IR. V equals E minus IR. No? V equals E minus IR. Subject current flow. Take this to the other side. Then IR equals E minus V. If current is subjected, I equals E minus VOR. No? Right. Now, let's apply this equation for these scenarios. Let's apply this equation for these scenarios. See what happens. First one, right? I1 for the first cell, I1, E1 minus, what about V? V is VAB. V is, it's VAB rather be VBA, right? Because plus and minus, no? Say VBA, that is VBA over R is R, right? First one is done. Then for I2, if you write, right, what happens? E2 minus same VBA, same potential difference over R. Again, for the third cell, I3 equals E3 minus VBA over R, right? Similarly, why don't we apply for the equivalent, right? Apply for the equivalent as well. Apply for the equivalent as well. Then capital I equals E dash minus VBA over R dash for the equivalent, right? Now, what we can do is, we know capital I equals I1 plus I2 plus I3, right? Total current inflow to a junction equals total current outflow from a junction, Kirchhoff's first law, right? Then my argument is this: capital I equals I1 plus I2 plus I3, isn't it? Capital I equals I1 plus I2 plus I3. For I1, I2, I3, we have answers here. For capital I, we have here, right? Then E dash minus VBA over R dash. I1 is E1 minus VBA. E1 minus VBA over R plus this is E2 minus VBA over R plus this is E3 minus VBA over R. Now, to do method of comparison, to apply method of comparison, both left hand side and right hand side should be exactly in the same format, same shape, same shape. Now, I'm going to make it to the same shape. Denominator is common anywhere. Denominator is common, R. Right? So, therefore, we can write this as, see, E dash minus VBA over R dash. This common denominator is R. Common denominator is R. If I take all these together, right, what comes is E1 plus E2 plus E3, no? See, E1 plus E2 plus E3. Then minus VBA minus VBA minus VBA means minus 3 VBA. Minus 3 VBA. Right. Now, we have to take this to the same shape. Here I have minus VBA only. Here minus 3 VBA. Right. Therefore, to take it to the same shape, I'm going to divide both denominator and numerator by 3. See what happens now? That is a possible application. Now, let's say you have x over y. You can also write x over 3 equals y over 3. We can divide both numerator and denominator by the same number. Doesn't matter. Doesn't affect the ratio. Right? Doesn't affect the ratio. So, I'm going to do the same. See what happens? Here E dash minus VBA over R dash. E dash minus VBA over R dash. Right? Here I'm going to divide whole numerator by 3. Then here what comes is E1 plus E2 plus E3 over 3 minus 3 to 3 cancels here VBA. Right? And this whole thing should be divided by R, and R is also divided, no? R over 3. Because if we are dividing by 3, both numerator and denominator should be divided by 3. Then here that is R over 3. Got it? Now, if you are not sure, you can simplify this again and see whether this comes. It comes. Right? Or make a simplify කරොත් I make it. මේක ඕන simplify කරලා බලන්න. මේක ආයි මේ 3 එක උඩට දාලා simplify කරලා බලන්න. ආයි අරගෙන. Right? Okay. Now we can compare. Now we can compare. See? Now we can compare. Now we can compare. I'll write the result here. Yeah. We'll write here. See? See what has happened? Now E dash is what has happened? E dash is E1 plus E2 plus comparison. No? E3 over 3. Right? This is method of comparison. Comparison. Right? E dash is E1 plus E2 plus E3 over 3, while R dash is R over 3. Right? So these two are the final answers. Right? So idea is basically this. This is E1 plus E2 plus E3, no? So when cells are in parallel combination, equivalent EMF is going to be the average of EMFs. If you have 4 cells, E1 plus E2 plus E3 plus E4 over 4, 5 cells, add all together, divide by 5. 2 cells, E1 plus E2 over 2. Right? So this is going to be the average value. Right? Very important. This is the average value of cells connected in parallel combination. Equivalent EMF is the average of EMFs of cells connected in parallel combination. And about resistance you already know, that is R over 3, because these 3 resistors are in a parallel combination actually. R in a parallel combination. So in parallel combination, if there is R, you have to add it as 1 together, 1 over together, right? 1 over R plus 1 over R plus 1 over R, it's going to result in R over 3. So it verifies about that resistance again, right? So this is a special proof, right? Special proof about the equivalent EMF in parallel combination and series combination. When it comes to cells especially, unlike other equivalents, this approach is a little bit different. So therefore, this is a very important, significant equivalent in our list of equivalents, right? So I hope it's clear. If there's anything, you can add a comment to the video and get it clarified, right? So I'm going to stop the video here. See you all in the next equivalent again with another video. Goodbye.